Hello and welcome to my presentation, AMAZE2, a no insulation HTS demonstrator coil for the Space Spectrometer Arcos. My name is Magnus Dam and I'm a postdoctoral fellow at INFN in Italy. The work described in this presentation is carried out within the HDMS collaboration agreement originally set up between CERN and the Italian Space Agency. HDMS is short for HTS Demonstrator Magnet for Space. The project has two goals. The first one is to make a conceptual design of a toroidal HTS magnet for a proposed magnetic spectrometer in space called Arcos. The second goal is to design and manufacture a demonstrator coil called AMAZE2 for the Arcos magnet. Arcos, which is an acronym for Astroparticle Research Compact Orbital Spectrometer, is a proposal for a next generation magnetic spectrometer in space. The spectrometer identifies particles by measuring their rigidity and electric charge. The spectrometer is based on a high-field toroidal magnet that bends charged particles traveling through the magnetic field. The basic detector system consists of a tracker which measures the charged particle trajectories in the magnetic field and a trigger to select desired event topologies. The rigidity of a particle is defined as the ratio of the momentum and the charge multiplied by the speed of light. The bending strength is a magnetic field integrated along the particle trajectory. A spectrometer with a higher bending strength is able to detect particles with larger rigidities. The average bending strength of the Arcos magnet should be 3 Tesla meters. The shape of the magnet is chosen to be a toroid, mainly because a toroidal magnet has a total magnetic moment that is zero. A zero magnetic moment is necessary to avoid unwanted rotations or drifting when the magnet is placed in space and affected by the interplanetary magnetic fields. The inner diameter of the toroid should be 0.5 meter to make room available for detectors at the center. The outer diameter should be no more than 2 meters to fit inside the rocket payload section. The straight segments of the coils are set to 1 meter. The operating temperature is set to 20 Kelvin, such that the magnet can be conduction cooled by a combination of a sun shield and an electrically driven cryostat. Other requirements are that the structure should be lightweight and sufficient space should be available for detectors between coils. The assumptions we made for the conductor for the Arcos magnet are that it uses HTS Repco tape that is 12 mm wide and 100 micrometer thick. The engineering critical current density is set to 1200 ampere per square millimeter at a temperature of 4.2 Kelvin and a magnetic field of 20 Tesla. With respect to angle dependency, this number is for worst case conditions. For most HTS tapes, worst case conditions correspond to the magnetic field being perpendicular to the tape surface. To obtain the corresponding critical current densities at other temperatures and fields, we use the fitting function that is here shown in a plot. The Arcos magnet consists of 12 toroidal coil packs with 2 winding layers per coil pack. The engineering operating current density is 855 ampere per square millimeter, with a peak magnetic field of 11.9 Tesla. The total length of HTS tape required for the Arcos magnet is about 62 kilometers, and the stored magnetic energy is 39.6 megajoule. The figure shows the magnetic field on the surface of the toroidal coils. On the inside and on the outside of each winding layer, there are copper bands attached to the first and last winding turns. The copper bands serve the purpose of transferring the current into and out of the winding layers. The mechanical structure consists of a magnet former and copper plates. The structure is made from aluminum to make the structure lightweight. The total force on each coil plate is directed towards the center of the toroid with a strain of about 4 meganewton. The equivalent stress is below 400 megapascal everywhere in the coil and the structure. The structure between coils consists of an inner cylinder that absorbs forces directed towards the center of the toroid, an outer hollowed-out cylinder that keeps the coils in constant distance from each other, and some additional structure that prevents rotational displacements. The second goal of the project is to design and manufacture a demonstrator coil for the Arcos magnet. The demonstrator is called AMAZE2, which is an acronym for Advanced Magnetic Spectrometer Experimental Demonstrator. By building AMAZE2, we want to properly test the technique of using copper bands as current leads and layer jumps, to manufacture and test a medium-sized no-insulation coil. We especially want to test self-protection against quenches and charging times for such a coil. And finally, we want to test the design of the aluminum structure. For AMAZE2, the requirements for the ATS tape is to have an engineering critical current density of 600 ampere per square millimeter at a temperature of 4.2 Kelvin and a magnetic B field of 20 Tesla. AMAZE2 has a racetrack-like shape and is a small-scale version of a coil from the Arcos magnet. The cable will be a tape stack of 2 ACS tapes. AMAZE2 requires a total of 750 meters of superpower ACS tape. The theoretical maximum engineering operating current density is 2480 ampere per square millimeters at 4.2 Kelvin with a peak magnetic B field of 9.3 Tesla. The coil will be tested at several different temperatures in the range from 4.2 Kelvin to 77 Kelvin. Copper bands surround the winding blocks. The outer copper band functions as a current lead and transfers the current into the first winding turn over the entire circumference of the winding turn. The inner copper band transfers the current out from the innermost winding turn and functions as part of the layer jump to the other winding layer. The mechanical structure for the coil is basically an aluminum plate with the shape of the coil machined into, enclosed by welded copper plates. G11 insulation encapsulates the coil layers. The current comes in through copper bands located around the winding layers. A copper block electrically connects the two winding layers. The stress in the coil block is everywhere below 88 megapascal. In the structure, the maximum stress reaches 259 megapascal, which is well below the yield strength of the material. We derived a simple circuit model to predict the behavior of the currents and mean temperature during charging, discharging, and in case of a quench. When the current enters the coil, it splits into a part that travels turn to turn radially through the coil and a part that travels azimuthally inside the cable. Only the azimuthal part contributes to the coil inductance. The azimuthal part can either travel inside the superconductor or in the normal conducting stabilizer material. The four equations in the upper box determines the currents, and the three equations in the bottom box determines the voltage drop over the coil, the mean temperature of the coil, and the peak magnetic B field. These figures compare solutions to the circuit model at operating temperatures of 77 Kelvin and 4.2 Kelvin. The operating current is first ramped up, kept constant for a while, and then turned off. The azimuthal current approaches asymptotically the operating current at all times. Turning off the operating current causes a negative radial current. At 77 Kelvin, the radial current is so low that it does not generate much heat, but at 4.2 Kelvin, the large radial current quickly increases the mean temperature of the coil to about 140 Kelvin. This shows how important it is to be able to control the turn-to-turn resistance in order to design a self-protected high-field magnet. Manufacturing the demonstrator coil actually includes the manufacturing of several coils. First, several small solenoids with different configurations are built. Next, 3 coils in the series called the Amazed coils are being built. Amazed 0 is a mechanical coil which has the superconducting tape replaced by copper-coated stainless steel tape. Amazed 1 is a single winding layer coil. It is meant as a practice coil. Amazed 2 is the final demonstrator coil. Amazed 0 has already been manufactured. We plan to carry out a few mechanical tests on it before proceeding with the manufacturing of Amazed 1. To summarize, the HDMS project has 2 goals. The first one is to make a conceptual design of the Arcus magnet. The Arcus magnet consists of 12 racetrack-shaped coil packs. The error rate bending strength is designed to be 3 Tesla and the peak B field is 11.9 Tesla. The structure is made from aluminum to be lightweight. The second goal of the project is to design and manufacture the demonstrator coil Amazed 2. Amazed 2 is a small-scale version of a single coil pack of the Arcus magnet. Amazed 2 is a no-insulation coil designed to be self-protected against quenches. The current status of the project is that the mechanical model coil Amazed 0 has been manufactured, and we will soon start manufacturing the practice coil Amazed 1.